This unit is going to be about linearization of a vector field or an ordinary differential equation at a critical point. One of the key things are at a fixed point. So we're going to suppose P is a fixed point of x dot is equal to f of x, right? i.e. f of P is equal to 0. And we want to understand the behavior of the dynamical system near P. That's what the next couple of units, in fact even the remaining 3 units are going to be about. The first thing to do, the first step, all right, so to understand behavior of dynamics near P, the first step is to look at the linearization of the vector field at P. Linearization of f at P, which is df of P. So this is what? An n by n matrix? It is the Jacobian matrix. And it turns out that the information, much or almost all of the information we need to understand the dynamics near P is given in df of P. Associated with df of P, we might also think about a dynamical system, right? So let's call it y instead of x, right? And that's y dot is equal to df of P times y. So this is a linear system, right? And what we do is we think of x dot is equal to f of x as giving rise to this y dot is equal to df of P times y, right? So x is in U, right, which is a subset of Rn, then y is going to be in Rn, and this is going to be a linear system. And this is the system. This system here is the one that is the linearization of this system at P. So what we can reasonably hope is that the dynamics of this system here tell us something about the dynamics of this system here. Right? So let's name these. Let's say 2 and 1. So the question is, to what extent does dynamics of 2 tell us about 1? Okay. Well, the first step is to understand the dynamics of 2. How do we determine all the dynamics of this? So we're going to deal with the dynamics of an n-dimensional linear system. Okay, so we want to understand the dynamics of this system here. We'll rename df of P A just for convenience. So it turns out that the dynamics of this system, right, which is the system 2 from the previous one, is determined by the spectrum of A. So 2 determined by the spectrum of A. So the spectrum of A consists of the set of eigenvalues of A. So these are lambdas, which are complex numbers potentially, so that the determinant of A minus lambda I is equal to 0. Those are called the eigenvalues of A, and the collection is called the spectrum of A. This determinant equation, characteristic equation, is an n-dimensional polynomial in lambda. You can figure that out. So that means that by the fundamental theorem of algebra, there are exactly n eigenvalues counting multiplicity. So the fundamental theorem of algebra implies there are n eigenvalues counting multiplicity. Okay, so there may not be actually n points in the spectrum, but if we count each of them by the multiplicity of the eigenvalue, that is the algebraic multiplicity of the eigenvalue, which is the number of times the associated factor appears in the characteristic equation, then they all add up to n. So the next step is to decompose the spectrum of A into 3 bits. sigma minus of A, union sigma 0 of A, union sigma plus of A. This is the set of eigenvalues lambda which have real part negative. This is the set of eigenvalues with real part 0, and this is the set of eigenvalues with real part positive. Using, for instance, Jordan canonical form, you can actually show that Rn will decompose into the direct sum of three subspaces, E minus, direct sum E0, direct sum E plus. Each of these is invariant under A, so each is invariant under A, and each somehow corresponds to the bit of spectrum. So the spectrum of A restricted to E minus is equal to sigma minus of A. So this means we could choose coordinates x is equal to u, v, w, where this is in E minus, this is in E0, this is in E plus, and you could see then that we could actually write it, we could in these coordinates write it as u dot is equal to A minus of u, v dot is equal to A0 of v, and w dot is equal to A plus of w. So we've somehow sort of decomposed it into three different pieces. Each of these may be of some, non-trivial dimension, but associated with each of them is an invariant subspace, because if v and w are 0, then which is on the u space, then it's governed entirely by the first equation. U dot is A minus of u. So we've got this picture that we've actually sort of decomposed the space into three pieces. We've got an E minus, E0, and E plus. Each of these is higher dimensional. It isn't necessarily in 3 dimensions. That's one example, but here is the origin, which is a fixed point of the linear system. And E minus is governed by this equation here. This governs the behavior on E minus. This governs the behavior on E0, and this one governs the behavior on E plus. Given that the real part of the spectrum is respectively negative, 0, and positive, you can say something about the dynamics on each of these spaces. So in particular, u of t is going to go to 0 as t goes to plus infinity. Right, that's clear. And in fact, it will do so exponentially. In other words, there exists an alpha such that the magnitude of u of t is less than or equal to some constant times e to the alpha t. And alpha is negative and the constant c is positive. Okay. Now then also by the same token, v of t is w of t is going to go to 0 as t goes to minus infinity, and will do so exponentially. But v of t may go to 0 or it may not. V of t has undetermined asymptotics, right? Has undetermined dynamics, basically. It could do a number of different things, but we know it does not go to 0 exponentially. But v of t does not go to 0 exponentially as time goes to plus or minus, either plus or minus infinity. But it may go to 0 because it may go to 0 algebraically. So we give names to each of these things. E minus is called the stable subspace. It's called the stable subspace. E0 is called the center subspace. And E plus is the unstable subspace. Okay. So as I've said, the dynamics on E minus are exponential decay. dynamics on E plus or exponential growth or exponential decay in negative time, and the dynamics on E0 is undetermined. Okay, so dynamics on E0 could be loads of things. So it could be like fixed points. They could all be living on E0. It could be periodic orbits. Or it could be algebraic decay. Right? There are lots of possibilities for that. So we want to prejudice that by saying one particular thing is favored over another. Okay, so that completes the unit on linearization.